Hello again. So this is like, I think my fourth video for this morning, and so I'm going to cut it off right here because I do have to start working on my house somewhere and put it back together. And, got to keep the wife happy, and me too, because the house is kind of like torn apart. Well, anyway, this video is going to be my last one for today. Tomorrow I'll go ahead and focus on some of the other stuff. I'm not going to get to the sun today. The sun is like the biggest thing that I want to share with everyone. But before I get there, I kind of have to explain. I feel like I need to explain how I got there. You know what I mean? Because it wasn't like I was like, hey, I'm going to wake up and start looking at the sun. No, it was like, damn it, I got to go back and look at the sun? God. Oh, man. Well, whatever. I guess I'll just go back and start looking at all the pictures of the sun and see what I come up with. And I'm like, oh, my God. Check that out. Oh, check this out. Oh, my God. And I'm like, okay, I got to start telling somebody about this stuff. Not that anybody cares, but I thought I would put it out there. And, well, I do know some people care. I mean, the people I talk to at work, they're very polite and have a lot of courtesy, and they're like, that sounds pretty, that's impressive. And I was like, oh, cool, why, thank you. Well, so, anyhow, we're going to go ahead and start looking at this particular slide. Okay, so earlier on, a few years back, I developed a spreadsheet that was something I referred to as the axial terra clock, and this basically took October 6, 2012, and put the Earth's axial tilt around the entire solar system throughout its entire orbit into kind of a clocked format as to determine what the Earth's axial tilt and axial cant would be at different times, at different intervals throughout its orbit around the Sun. But you see this, just like our equinoxes change and our solstices change and things of this nature, the axial terra clock would change. So, it doesn't really change a lot, I don't believe, but it does change. So 2010, I just use it as the base model. And then I'm like, you know what? If I'm really going to come up with a solid confirmation for what the galaxy's obliquity or its angular momentum is in relation to the AGC 203001 event horizon of the theoretical wormhole, I might need to go back and reconsider and replot a current axial terra clock. And then I got off on a major tangent because I was like, I'm still not comfortable that I know exactly which way the Earth is tilting in relation to what direction of what. So here's my internet capture on that one, screenshot for here for the hottest time of the year, and then Saturday, March 20, because I want to get the spring equinox is where I want to go. I want to be on the galactic anterior, looking in toward the center of the galaxy, because that's where I expect to find the best illustration of the flight posture of everybody, the Earth, the solar system, and the galaxy. Well, the Earth and the solar system in relation to the galaxy before we worry about what the galaxy is doing in relation to a wormhole. All right, so I'm going to go down here. This is a photograph taken by Mr. Dave Morrow, and I thank God for people like Dave Morrow who, half the time, in a sense, he's every bit of a sniper, only he's a sniper with a camera rather than a sniper with a rifle. So he's out there freezing his freaking whatever's off and waiting for the perfect photograph. He might not even get that photograph, but this man is hard. He's a hardcore. He is tough. He's a tough dude. He goes out there and he gets that photograph. He's awesome. I love that guy. And here's the photograph. So I take it from here. Here's my side aperture, that little dip in the mountain right there. From his observer point, I had to go off on over here to the left where you can't see. I used Google Earth to calibrate my reticle pattern so that at this distance from this position on Mr. Morrow's OP, I have my reticle set for that distance. And it's geometry and math all the way around. Okay, this was October 6, 2012, and I did all that stuff. And I'm going to go down here. Now, you'll notice that up here we have, I'm sorry, I went back. Here's known point 1. Originally, I just went with known point 1. Then I decided, you know what, if I'm going to really accurate about this stuff, I need more than just one known point. I need 3 known points. So here's known point 1. Here, well, we'll go down to the next slide. Well, I guess I didn't number them. So this guy is known point 2, this one right here, and then this one right here is known point 3. Okay, my 3 known points. I come down here. It's another photograph of somebody standing out here around wherever the hell this is. And oh, well, they're Mauna Kea. Okay, and these 2 telescopes shoot lasers right out here to bam, what appears to be the center of the galaxy, right? And it is. And then you notice that this is the base of the galaxy, and this is the head of the galaxy up here. So the bulge is smaller here, greater here, and you have known point 1 there, you have known point 2, and known point 3. All right. Now we're going to this. I have known point 1 here, known point 2, oops, and known point 3. And now, when you look at this particular composite presented to us by the ESO, a European Space, somebody or other, organization, yeah. And you can see that from about this point right out here to this point right about out here somewhere, you follow that. This, ladies and gentlemen, is a very gradual arc. It's called a conical shape. So our galaxy, even though it's kind of got the wings, like it kind of has like the wings of a stingray, right? You got the body of the stingray and its wing, and it comes down and its wings go up, right? It's kind of like what we have here. We kind of have this little W shit going on. And right underneath of here, we have the conical shape of the base of the galaxy. And that's what's actually being, the greatest force is right there. And then it just kind of like curls up as you get farther out to the galaxy, where the forces that are basically rotating our galaxy, the universal force rotating the galaxy, is giving it that shape, okay? And the highest bulge up here. So we live kind of like up here somewhere in this galactic Virga. So you see all this weird stuff kind of floating up away from the galaxy and floating down away from the galaxy. Yeah, that's what I refer to as galactic Virga. So now, in my recent studies of the sun's corona, we have solar Virga, studies of the Earth, we have continental Virga, studies of the galaxy, we have galactic Virga, and then of course you just have ordinary Virga that comes from rain clouds, or nimbostratus and stuff like that. All right, then we come down here. Here's my my above view that was given to us by NASA, and we have the sun's location here in the Orion Spur, and then off over here to the left we have known point 1. Okay, and bam, there it is. You've got the center of the galaxy here, and here's my tangent, equals 76 mils, equals 4.3 degrees, right there. Okay. And we go to the next slide, and that gives me, basically from this view, in Google Earth you can see the galaxy back here on this particular galactic attitude. And the attitude, it is not a person's bad attitude. Okay, we're not talking about like the galaxy has a bad attitude or a good attitude. The attitude is a direction. And basically, if you have a circle like this, I'm going to show you right. Here's my circle. This is my compass. And up here is 0. Right there is 0. And the attitude is the direction measured from 0 to the right all the way down to 200 mils or 180 degrees. You only ever give an attitude measured toward the right in that one hemisphere of a compass. Why? Because you're describing a linear object that marks one side of your compass, and obviously whatever's marked over here is followed by an opposite mark, opposite yet equal mark on the opposite side of the compass. So you only need to measure one direction on one hemisphere of the compass. That's your attitude. So my galactic attitude is right here, and that's my blue line that I threw here. Now you'll notice that the way that I have the Earth oriented, my particular azimuth of the red line from Sunrise Point is going in exactly like the opposite direction. Well, if you flip the planet around, it's going in the right direction. And you're still at, oh, by the way, here's the North Pole at approximately 25 degrees above the galactic plane. Ba-bam! All right. And there you have it. 27 degrees in this particular instance. Excuse me. All right, so the next one here, there it is. There, I flipped the planet around so it looks a little bit better. So if you were to like take the center here and draw it to the center there and take it out the other side, basically this galactic center position here is cutting right through the middle of the planet. All right. Now I'm going to go back and let's see. Is it this one? Now I'm going to read this to you. Above is Dave Morrow's photograph. In this photograph, we cannot see the MOG's bulge. Assuming the NASA compilation of the MOG is likely viewed from above and the MOG rotating clockwise, this indicates the supermassive electromagnetic gravity waves, SMEGAWs, are sweeping from behind Dave Morrow's observation post toward the galaxy as we see here. The base of the MOG is on the left side of this photograph. Base, left side. All right. With this photograph, the base of the MOG is clearly on the left because it's like over here. All right. Now we want to identify known point 1. Known point 1 on this photographic compilation from the ESO. Again, all right, I can't read my own writing. Okay, again, based upon the other two photographs, we will find known point 1 somewhere to the left of the galactic bulge. By the way, this is the galactic bulge because that's where it bulges. Okay. And then we go to the next slide. I didn't put any notes there. Then we go to the next slide. After reviewing slides 9, 10, and 11, I can see that the Earth and the MOG are in line as they should be. Okay, so things are turning out pretty good for us there. The Earth's North Pole orientation is consistent with the surfboard gliding along a wave and not oriented as a nose cone of the engine of a black bird. That, you know, that really fancy, beautiful aircraft that we built is like, it is so awesome. I love that bird. Anyway, its engine's going to go like this, right? From your point of view, they're going in toward the freaking nose cone of the aircraft. And because it flies like this, you know, just like that. It makes that noise too. I know, I was there. When I viewed the Earth backdated to October 6, 2012, around October 2019, from this perspective, I should not have been able to see the galaxy as I do here. The galaxy would be behind my observer position, not in front of it at a greater distance. All right, so I was a little bummed. Today is May 8, 2021, 5:04 a.m. Google Earth presents the galactic attitude to be at approximately 27 degrees below the North Pole. It is currently before morning nautical twilight, BMNT, outside. I cannot see the galaxy at all. I do live in the Pacific Northwest. And often cannot see beyond the clouds. I can, however, see one star. I have no clue which star that is. In this view, Google Earth displays the galaxy to be at a greater distance than the Earth from the observer's position. What will happen when I rotate the view of the Earth with the sunrise point, OTL, on the other side? All right, did I do that? Yeah, probably. Well, I did, and blah, 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 there it is. Okay, now, from this view, America is peering off into space outside of and beyond the galaxy. When I set Google Earth back in time to October 6, 2012, the galaxy appeared to set the solar system on the wrong side. This may possibly have been because of a glitch in the program's older algorithm. I sent Google Earth a request asking them if they would kindly place the galaxy on the other side of the solar system. I'm not certain they took me seriously. Oh, would you take me seriously? Excuse me, would you please place the galaxy on the other side of the solar system? God. Alright, anyway. Okay, we talked about that one, I think. Okay, here we looked at this. Oh, look, there's a spot. Alright, there's that same spot. Alright, now. Oh, that's what I'm doing. I'm figuring out a good angle here so that we can see the Earth's flight posture with the did I type anything into these notes here or anything like that? No notes on that one. No notes on that one. Okay, so anyway, we have a 25-degree angle, vertical angle above the galactic attitude here. And here's known point 1, here's known point 2, and here's known point 3. And Orion's belt is somewhere out here. Okay, well, Orion's belt. Yeah, Orion's. Oh, right. Yeah, I think that was Orion's belt right there, possibly. I mean, it looked like they were in the same orientation, sort of. All right, now in this view, I'm looking at it, and I have known point 2, known point 3, known point 1 up here in the center of the galaxy, and trying to basically show us where the center of the galaxy is in relation to my views here, and here you can see the bulge just beyond Earth. Okay, then I go here, and now I have the center of the galaxy. I'm showing you how it's angled right here. I come up with where it comes cross-haired on the Earth, and I'm not really sure why I did that. Alright, and then I'm showing more about this stuff in relation to the Earth. I guess basically I'm still showing you how how I'm proving to you what the Earth's galactic flight posture really is. And here we go. Got another one right there. That X marks the spot, yo. Ooh, here we go. What's that? Where'd it go? There we are. Okay, this one here. What's on this one? All right, no notes. Okay, now we're measuring distances from the center of the Earth right here to basically the center of the galaxy, and that's going to pretty much tell us what the obliquity of the Earth's equator is in relation to its galactic flight path. And so what I'm really boiling it down to is here, I'm telling you that, as you can see right here, when we're looking at this stuff, right? Let me go back up here. Right here. This is the North Pole pointing toward us. It's closer to us than it is farther away, right? And that's kind of how it is in relation to the galaxy. It's not pointed like a nose cone on the Blackbird in toward the galaxy's center. It's on an angle pointing away from the galaxy as it's going around, and it's above the galactic plane. Here's the galactic plane. It's doing this. These fingers, the fingertips, represent the center of the galaxy. It's going around the merry-go-round. Because as the Smeagol's sweep, they come around from the right, they hit here, they hit the opposite corner of the planet first, sweep down underneath, and they're coming down like this and passing out on top and going out like that, and at the same time they're rotating the planet. So you not only have the solar wind pressure from the sun rotating the planet, you also have the Smeagol's helping assist in rotating the planet, as they are the forces that gave the sun its original rotation. All right. And we're moving on down the line here. I'll get to my notes. Got notes down here somewhere. All right, doing all the measurements, blah blah blah. I sent this stuff to NASA already. Don't know if they're making anything out of it yet. All right, so down here I basically have a whole bunch of stuff that I'm writing about, and if I bring this up, I'll go ahead and read it to you. I know this is boring when I read, especially when I can't even read my own writing. Google Earth does not allow the user to set the Earth's tilt into a negative view. The positive tilt positions the North Pole's axial cant away from the observer. Therefore, I can only set the planet on a heading of 39 degrees. Then I have to manually adjust the observer's view at I guess I did that wrong. At an approximate 27 degrees cant. This view is from a point above the galactic plane looking down. The Earth's North Pole can just be seen peering over the northern horizon. The equator illustrates the Earth's axial cant in relation to the center of the galaxy. We can see here the equator on the right side of the planet is set at a position above the equator on the left side of the planet. The equatorial ellipse illustrates the planet's axial tilt at 27 degrees. The axial tilt at 27 degrees, as seen from above the galactic plane, indicates the far side of the Earth rests farther forward than the near side. This appearance is due to the Smeagol's sweeping into and beneath the Earth as they push it forward on its galactic flight path. The Earth is confined to the solar system orbit along this galactic flight path. The east equatorial horizon, positioned above the west equatorial horizon on a 39-degree cant, illustrates how the Smeagol's strike the galactic interior flank of the planet first. The Smeagol striking the galactic interior flank of the planet is due to the formation of spiral density. Since spiral density waves only refer to stellar clutches, we will not describe Smeagol's as spiral density waves. It is the Smeagol's, however, that form the stellar clutches appearing as spiral density waves. From this view, we can understand that it is the parent black hole, PBH, on our side of the galaxy that rotates the Earth and our solar system. The solar system vortex already formed as a differential rotating celestial body long before the sun fully accumulated at the center and ignited. Upon solar ignition, the solar system would have been given an accelerated rate of rotation faster than the universal rotation rate of 9 Jupiterian stripes, for example, 13 Jupiterian stripes. Therefore, when the vortex, which somewhere along the line I probably put out a video for the vortex, well, we'll get back to that too, began to solidify along the Earth's planetary suture. The Earth's planetary suture is the mid-Atlantic ridge. That is the mid-Atlantic ridge. Yeah, there, I wrote it down too. 1 Earth day was equal to 16 hours. Then, at some point between the date the planetary suture sealed the Earth's surface and today, 1 Earth day was equal to 20 hours. So we have a scored record for 13 Jupiterian stripes at 16 hours. Then we have another scored representation for 20 Earth hours. And of course now we have a 24-hour rotation, which seems to be more consistent with the Jupiterian 9-stripe rate of rotation that we can see throughout a lot of things. And that's what I'm saying is basically what gives us our angular momentum of the average 25, 27 degrees. So it may be a greater relation, a constant that you can find between solar systems, between galaxies, within our universe, because the universe has a rate of rotation that affects our rate of rotation. All right, that's that point. Oh yeah, okay, put it back down like that. All right, and that was my last slide for this one. So I never really did get back to redeveloping a new, more updated axial terra clock. Don't think I need it. And then, of course, I started to veer off and begin looking at the sun and analyzing the sun until I got off on a tangent on analyzing the sun because it began to look more like the Earth. Not the flames, the convection. All right. And that concludes my slide presentation for this one. Death by PowerPoint. Yeah! Okay, so please like and subscribe if you like to listen to boring astronomical weird stuff.